Welcome to This Explainer. Look, in a world where devastating perimeter breaches can happen in, mere seconds, we are going to skip the industry buzzwords today. Instead, we're laying down the actual, practical blueprint for programming a dynamic zero-trust architecture right in Python. So, if you're tired of hearing zero trust talked about as this vague, high-level concept, and you actually want to see the math, the logic, and the code that makes it tick under the hood, well, you're in exactly the right place. Let's get into it. Our anchor principle here is pretty simple. Never trust, always verify. But actually operationalizing that, that's incredibly complex. We are totally abandoning the old castle and moat security model. In the architecture we're exploring today, every single network request, whether it's coming from completely outside the perimeter or from the exact same server rack right next door, has to actively earn its access through continuous, rigorous verification. So here is our roadmap for today. We'll quickly touch on the zero trust philosophy, build out our domain schema, map the network graph, wire up the dynamic policy engine, and finally, we'll put it all to the test by simulating a high-stakes insider threat. All right, part one, the zero trust philosophy and setup. Let's start laying the foundational concrete for our Python environment. Before we build the walls, we obviously need our tools. This setup phase is all about grabbing our dependencies for graph modeling, risk scoring, and API handling, but the real heavy lifting happens with the utility functions we define right out of the gate. We're setting up trust normalization, cryptographic hashing, and timestamping, and crucially, we implement weighted sampling. Now, why is that specific detail so absolutely vital? Well, it ensures our simulations are completely deterministic rather than just purely random. When we run our stress tests later, we need to know the outcomes are based entirely on our policy rules, so we can accurately benchmark them against repeatable scenarios, not just random variance or noise. We also prep helper functions to spit out structured JSON logs, which guarantees every single decision is perfectly traceable.
Okay, moving on to section 2. Let's build the domain schema.
We have to bring order to the chaos of network traffic by establishing a rock-solid foundational data model. By using Python data classes, we're formalizing exactly what a zone, an asset, or a role actually is in the code. We're explicitly defining the structures for network requests, security decisions, user principals, and devices. Setting these up as frozen data classes is a real game changer because it guarantees immutability. Basically, once a state is recorded, there is no way it's getting accidentally overwritten during runtime. Without this rigid schema, your application literally cannot evaluate trust continuously. Think of it as the exact, non-negotiable vocabulary our system uses to judge every identity and device across thousands of network paths a second. Section 3, mapping the network graph. With our vocabulary locked in, it is time to build the walls. Now, we aren't just drawing a static map here. We're constructing a highly complex, micro-segmented, directed network graph. Think of it in terms of nodes and edges. We explicitly model our zones and assets as nodes and assign really specific sensitivity attributes to them, like tagging a database cluster as mission-critical. Then we programmatically generate interzone and service-level communication paths to act as the edges, simulating realistic enterprise traffic. As we map this out, flowing naturally from user access down through the application layer and into the secure data tier, we establish strict mathematical segmentation boundaries. This lets the system instantly anticipate and mathematically choke off potential lateral movement routes before a threat actor even has a chance to exploit them. Next up, Section 4, the dynamic policy engine. Time to wire up the security cameras and the guards. This engine is the absolute brains of the operation. Every single request gets routed through here and evaluated against a flood of live, contextual signals. We kick things off with a baseline score using traditional attribute-based access control, or ABAC. But then the math of our weighted risk model kicks into high gear. It adjusts that baseline in real time based on device posture, MFA status, and behavioral anomalies. For instance, a slightly unusual login time might just shave, say, 5 points off the trust score, but a critical failure, like an invalid MFA token or an impossible geographic jump, that carries massive mathematical weight and might completely tank the score by 50 points or more. The engine processes all of this instantaneously to compute a continuous living trust score. And you've got to see how the system reacts. Based on that continuously computed score, it doesn't just hand out a lazy static yes or no. It dynamically updates the device and the user's state to trigger adaptive controls. If the score dips just a bit below optimal, boom, it prompts a step-up authentication challenge to re-verify who they are. If it drops further because of repeated anomalies, it strictly enforces rate limiting to slow down potential enumeration attacks. And if the behavior mathematically screams threat, it triggers an absolute automated quarantine. This is how you prove the architecture truly never trusts and always verifies, reacting with precision based on exact data. Finally, Section 5, Simulating Insider Threats. We've built our fortress, modeled our graph, and operationalized the policy engine through a Flask API. So now it is time for the ultimate stress test. What actually happens when a trusted insider attempts lateral movement? This is the nightmare scenario, right? Considering insider threats make up a massive chunk of major data breaches, it's the perfect test for our engine. We've got a trusted employee on a managed corporate device already deep inside the network who suddenly goes rogue. To make this realistic, we generate some incredibly noisy mixed traffic. We run normal day-to-day business activity right alongside malicious external flows and the insider's sneaky lateral moves. We cleanly contrast this by injecting contextual variables right into our Flask API endpoints, basically passing JSON payloads that simulate this disgruntled employee abruptly changing their geolocation, spiking anomaly scores, and trying to pull massive data transfers at 2 in the morning. We run these as multi-step simulations to see exactly how our algorithm handles cascading evolving risks in real time. Let's watch how this unfolds stage by stage. In stage 1, the insider logs in normally. The math checks out, the trust score is high, access is granted. Easy. But in stage 2, they trigger an unusual geo-risk signal via an API payload. The engine mathematically catches the anomaly, instantly drops the trust to medium, and dynamically forces a step-up MFA challenge. The insider passes it, sure, but now they are heavily monitored. Stage 3, they attempt a lateral move, a strict path violation, trying to snoop in a highly sensitive zone. The trust score plummets to low, and the system instantly rate limits their connection to an absolute crawl. Finally, stage 4. They get desperate and attempt exfiltration, pulling a massive volume of data from the restricted tier. The trust score hits absolute 0. The engine automatically quarantines the user and aggressively severs the edges in the network graph to stop any further movement. The threat is completely neutralized. So the biggest takeaway from this explainer is that modern security is far more than just throwing up a static firewall or requiring a simple VPN connection. When you combine rigorous graph-based segmentation with an evolving trust score and highly automated responses, Zero Trust becomes a measurable, entirely programmable loop. We now have a repeatable Python framework that we can easily extend with richer telemetry, advanced machine learning anomaly models, and custom environment-specific security policies. Which leaves us with this final thought. We've just seen how identity, device state, network context, and complex behavior signals can all be evaluated together programmatically for every single interaction. So as you evaluate your own architecture, ask yourself, is your network truly verifying every single action with a continuous programmatic loop? Or is it just relying on a static perimeter and, well, hoping for the best? Think about how you might apply this engineering blueprint to dramatically harden your own infrastructure. Thanks for joining me on this explainer, and keep building.